Hi everyone, and welcome to Chapter 4, Lecture 1. This lecture is going to be on properties of solutions, which may be review from last year, so from first year chemistry, but I just want to make sure that we cover all of these definitions and terms and even the process before we go into the solution stoichiometry and net ionic equations. With solutions, the solution is defined as a homogeneous mixture of two or more pure substances. So a lot of times what we see with solutions is a solid being dissolved into water typically. With the solution, the solvent is what is present in the greatest abundance. That is what you have the most of. The solvent is what does the dissolving. Typically for us, we use water. You'll also see it could be methanol, ethanol, another alcohol, but typically it's going to be water. The other substances are the solute. Again, the solute is what gets dissolved. Typically it's a solid. If you think about Kool-Aid, solute would be the Kool-Aid powder, solvent would be water. Now with solutions, when water is the solvent, this is when we can consider it an aqueous solution. So when you see aqueous solution, that automatically tells you that water is the solvent. So we talked about water being a solvent. Now water is a very, very good solvent for ionic and polar compounds because it itself is polar. Now you may have heard the term or the phrase like dissolves like. Although this is a very useful guideline for determining if something is soluble, it is not an explanation. So if you are asked to explain some question or you're asked to explain your answer, you cannot simply say like dissolves like. What you have to do is you have to address the electrostatic aspect of the solute-solvent interactions. What I mean by electrostatic aspect is that negative ions are attracted to the positive hydrogen and the positive ions are attracted to the negative oxygen. Okay, this is the idea of the opposites attract. So this is what looks like an S positive, it means partially positive. This, what looks like an S, is delta. So delta plus means partially positive. This delta with the minus means partially negative. As we talk about aqueous solutions, it's important to know that substances can dissolve in water in a couple different ways. First, we can have an ionic compound. An ionic compound dissolves by the process that is known as dissociation, where water surrounds or solvates the separated ions. Now, we get this process of dissociation because the solvent, typically water, pulls the individual ions from the crystal lattice, and that is what you can see down in this figure. So we actually see the water molecules coming up to the sodium chloride crystal and actually pulling each ion away by those electrostatic forces that we talked about. So the negative oxygen is going to be surrounding the positive sodium, and the positive hydrogen will surround the negative chlorine. And this, again, like I said, solvates the ions. It surrounds itself with water. Now, molecular compounds, they interact with water, but most molecular compounds do not dissociate. They might dissolve, but they do not dissociate. When you see the term dissociate, that means it breaks down into ions. Molecular compounds don't have ions to break down into. Instead, what happens sometimes is these molecular substances react with water, and that is actually what we see occurring. In the resource video section on the class website, there are actually a lot of videos that correspond to each of the lectures in this chapter, and one of them shows the process of dissolving sodium chloride in water. So I would recommend you take this time, it's about a minute and a half, to go onto the class website and actually watch this video. Going along with solutions and talking about dissolving, we're going to look at electrolytes and non-electrolytes. So an electrolyte is a substance that dissociates into ions when it's dissolved in water. So when you put an electrolyte into water, it dissociates into ions, so you have mobile charged particles moving around. Okay, mobile just means they're free moving. So when you put sodium chloride into water, it dissociates into Na plus and Cl minus. So you have those charged particles moving around in solution. And the more mobile and charged particles that you have present, the higher the concentration of ions in solution, and the more likely it is to conduct electricity. So when we think about electricity, okay, electrolyte, electricity. So electrolytes conduct. The extent to which a solution conducts depends directly on the number of ions that you have present in the solution. Now, on the other hand, we have a non-electrolyte. A non-electrolyte might dissolve in water, like sugar, but it does not dissociate into ions, which means it does not conduct electricity. So if we think about what we talked about here and what we talked about when we talked about aqueous solutions, electrolytes typically are ionic compounds. Non-electrolytes are typically molecular compounds. There are going to be some exceptions, but we'll talk about those later. Again, in the resource videos section on the class website, there's a video that's titled Electrolytes and Non-Electrolytes. So please take this time, go watch that video. It does a great job of distinguishing between the two and describing properties of each. So continuing our discussion about electrolytes, a strong electrolyte dissociates completely when it's dissolved in water. So when you put a strong electrolyte into water, it dissociates completely, which means it conducts electricity. Strong electrolytes are any soluble ionic compounds. So what that means is potassium, nitrate, ammonium, sodium, all of those are soluble ionic compounds, any ionic compound that contains those. Also, strong electrolytes are strong acids, strong bases, anything that dissociates 100% in water and conducts electricity is a strong electrolyte. A weak electrolyte only partially dissociates when it's put into water. Typically, weak electrolytes only dissociate about 1%. Which means if you're given a particle diagram, a weak electrolyte is one in which you have some ions, but you still have a lot of the initial compound. And then you have a non-electrolyte. So a non-electrolyte does not dissociate in water. So again, check out the resource videos for this chapter because you have one on strong and weak electrolytes that will distinguish between the two and give more properties of each. Soluble ionic compounds tend to be electrolytes. So when you have a soluble ionic compound and you put it into water, such as sodium chloride, it will dissociate into its ions and conduct electricity, making it an electrolyte. However, not all ionic compounds dissolve in water. What you have to do is you have to look at the solubility rules to decide if it will dissolve or not. Memorizing the solubility rules is going to be extremely important for you throughout the entire year of AP Chem. You have the list of solubility rules in your summer packet. You also have it right here on the screen, and it's table 4.1 in your book. You have to memorize these. I cannot stress that enough. In the summer packet, you will see that it says potassium, nitrate, ammonium, and sodium are always soluble. That's a good place to start if you memorize those four, but definitely knowing this table is going to give you a leg up as you work through all types of problems. Non-electrolytes. Molecular compounds tend to be non-electrolytes with the exception of acids and bases. Okay, so all molecular compounds are usually non-electrolytes, meaning that they don't dissociate, except for acids and bases. That's that exception that I was talking about. Non-electrolytes may dissolve in water like I talked about, but they don't dissociate into their ions. The only time that you would have any dissociation or even partial dissociation is when we look at acids and bases. Those are electrolytes. When we describe acids, we have to think about a couple different definitions that some chemists have developed. So first, the Swedish chemist Svante Arrhenius defined acids as substances that increase the concentration of H plus when it's dissolved in water. What that means is the Arrhenius definition defines an acid as something that starts with H. So HCl, HBr, H2SO4, those all start with H. Arrhenius definition says that those are acids. However, Bronsted and Lowry came up with their own definition and defined it as a proton donor. This is where we get into the Bronsted-Lowry reactions, and we'll do a lot more of that when we get into acids and bases. But it is important to know that acids can be defined a couple different ways. Acids are molecular compounds. They do not have metals in them. Therefore, they do not dissociate into ions. The only time you have dissociation is when you have an ionic compound. However, there is a reaction that occurs between an acid and water when you mix the two. What happens is we have the process known as ionization. So the acid is ionized, not dissociated. What happens when we put this acid into water is we form the hydronium ion, which is H3O+, and the anion. So because of this ionization process, acids are considered electrolytes. Bases, on the other hand, are usually a compound that contain a metal with a hydroxide. So the Arrhenius definition of bases says that substances that increase the concentration of OH minus when dissolved in water is a base. So he said acids have H plus, bases have OH minus. Bronsted-Lowry definition says that bases are proton acceptors. Again, we're going to get more into these definitions when we get into our acid-base unit. However, it's important to know these simple definitions right now as you work through. So typically a base is going to be a metal attached to a hydroxide with the exception of ammonium, which is NH3. With acids and bases, it's important to know the distinction between a strong acid and a weak acid, or a strong base and a weak base, because strong acids are strong electrolytes, weak acids are weak electrolytes. So strong acids completely dissociate in water, where weak acids only partially. And then the same thing with strong and weak bases. It is very, very important that you know your 7 strong acids. You have HCl, HBr, HI, HClO3, HClO4, HNO3, and H2SO4. So those are your strong acids. Everything else is weak. Same thing with your strong bases. Strong bases are any in the alkali metals, all group 1, then calcium, strontium, and barium. Now, if you think about these bases, if you look at your periodic table, your bases actually make a lowercase b on the periodic table, right? Everything in group 1 and then group 2, part of group 2. Beryllium and magnesium are not strong. So we have, again, every alkali, group 1, calcium, strontium, and barium in group 2. I provided this table for you just to show you common acids and bases that you will see as you do work in stoichiometry or in acids and bases. Really anything in chemistry, these are going to be common acids and bases that you will see. So the strong acids we already talked about, same with strong bases. So strong acids and strong bases are strong electrolytes, weak acids and weak bases are your weak electrolytes. One thing to make note of is ammonia, NH3, very, very common weak base. Anything that is not a strong acid is weak. So these are just some. You can have HF, you can have quite a few different weak acids. Anything that is not strong is weak. So to summarize, soluble ionic compounds, which are also called salts, dissociate into ions. They go through the process of dissociation or solvation in order to dissociate into ions. Anything that dissociates into ions 100% is a strong electrolyte. If it dissociates into ions only partially, it's a weak electrolyte. Bases that contain a metal with a hydroxide will dissociate into ions unless it is insoluble. Acids are ionized, not dissociated. They are ionized into H plus ions, or H3O plus, and anions. And the base ammonia, which is NH3, is actually partially ionized. So we should make sure that we put partially ionized into NH4 plus and OH minus. So again, this is a summary of some of the different reactions that we talked about in this first lecture. The second lecture, we will go through some types of reactions that happen in solution, and then in the final lecture, we will talk about solution stoichiometry. Be sure that you take a look at those resource videos to help you out, and if you have any questions, let me know.